Hello everyone, my name is Dr. Lauren Spirko-Burns, and today I'm going to speak to you about unified methods for feature selection in large-scale genomic studies with censored survival outcomes. This is joint work with my collaborator, Dr. Kartik Devarajan. A little overview of my talk. I'll start with an introduction and literature review, and then I'll discuss various proposed methods for feature selection and ranking, and look at some simulations and real data examples, and then conclude and discuss future work. A little background on this problem. A major goal in genomic studies is to identify genomic features with the prognostic impact on censored time to event outcomes. With the rapid development of genomic technologies, the expression levels of tens of thousands of genomic features can be measured, thus creating enormous amounts of data. Examples include studies of gene and protein expression, such as microarrays, methylation, next-generation sequencing, and more. So being able to identify features, possibly with time-varying effects, associated with a censored survival outcome of interest could help provide insight into disease prognosis and treatment. The problem is that methods based on univariate Cox regression, which assumes proportional hazards, are often used to select features related to survival outcomes, and we'll talk more about why that's a problem. So some background, the type of data we're talking about presents three explicit challenges. The first one is that the number of covariates is far greater than the number of observations. The second is the presence of censoring. And the third is the presence of non-proportional hazards. So the pH assumption is unlikely to hold for each genomic feature or for combinations of several features of interest. And when the Cox pH model is applied to features exhibiting some form of NPH, it could lead to an under or overestimation of the effects. So in this talk, we propose various feature selection methods that attempt to address the potential for non-proportional hazards. The survival notation I will use throughout this talk, N is the number of subjects, P is the number of covariates. We have capital Z, the gene expression matrix, Z is a P vector of covariates, P is our survival time, and we have the density, survival, and hazard functions. C is the censoring time, Y is the minimum of T and C, which is going to be the observed survival time, and therefore we have delta, which is that censoring indicator. Delta equal 1 means the event occurred, and delta equal 0 means the observation was censored. So the first thing we want to talk about is how to model survival data. And the first model we'll discuss is the Cox proportional hazards model, which is one of the most popular. So it has the following hazard rate at time t for an individual with feature Z. You can see the form here. Beta is estimated by maximizing the log partial likelihood. PI is the survival time for subject I. Delta I is the censoring indicator, and that R is the risk set at time TI. Now, the problem is that this model assumes that the hazard ratio is constant over time, which is evidenced from the hazard ratio that you can see here between two individuals with features values Z and Z star. You can see this is completely independent of time. The problem is that this pH assumption is unlikely to hold for all P features in a genomic data set. So there's an inherent need for alternative models in this application. The two alternative models we're going to talk about are first the proportional odds model, and you can see it has the following form. This assumes that the odds of dying or recurrence at time t given covariate Z is proportional to baseline odds. Its parameters are estimated by maximizing the modified partial likelihood. And there's also a more general version of this model called the proportional log odds model, PLO, which we'll also refer to as CO. You can see the form here. When gamma equals 0, it refers to the PO model, and then we'll also look at a special case where gamma equals beta. The last model we want to discuss is the Yang-Prentice model, which is actually a generalization of both the Cox and the PO models. You can see its hazard and survival functions here. And if you set gamma equal to beta, it actually becomes the Cox model. And when you set gamma equal to 0, it becomes the PO model. So it's very versatile. Now, before we begin, we'd like to look at some motivating data examples. And I have the 5 data sets we're going to look at listed here with various types of genomic data. The first one involves DNA methylation data. The second is microRNA expression profiles. The third is digital gene expression profiles obtained using RNA sequencing. And the fourth and fifth are microarrays from patients with ovarian and oral cancers. Now, the first process we looked at is we wanted to just explore the data. So we decided to fit the models previously described, the pH, PO, and YP models, to check model significance and goodness of fit. The estimation procedure for the YP model only allows for dichotomized covariates. So in that particular case, we had to dichotomize the genomic features by the median. And then for comparison, we also ran the Cox and PO models that dichotomized data. So we'll have both continuous and dichotomized results for the Cox and PO models. For any continuous genomic feature in the Cox and PO model scenarios, we adjusted for the clinical variables age and stage. And the ultimate goal here was just to explore and try to identify features that exhibit some form of NPH and demonstrate the real need for alternative methods to the Cox model. Now, all the results you'll see on the next two slides are based on raw p-values, but Story's q-value was applied to account for multiple testing. So here you can see a summary of model fits using quantitative, the continuous features across the 5 data sets. And the first thing we want to highlight is that the pH model does not fit a large fraction of genes, particularly in data sets 2, 4, and 5. And then if we look at the PO fit, we can see large fractions of those features are fitting the PO model across all 5 data sets. What's particularly interesting is if you look at the subsets A and B, this is where the PO model fits and the pH model does not fit. And you can see a large fraction of the features for which the pH model does not fit. The PO model is providing a nice alternative and fitting a large fraction of those particular features. We see very similar results for the dichotomized setting. So in this case, again, the features were dichotomized by the median, and then the pH, PO, and YP models were fit in those cases. And again, across the board, we can see, particularly in data sets 1, 2, 4, and 5, a large fraction of the features do not fit the pH model, therefore violating that pH assumption. Where you can see the PO and YP models are offering a nice alternative. Over 90% of features fit those models in each case. And the YP model, the numbers are particularly high in data sets 1, 2, and 3. And then again, if you look at the intersections, you can see that the PO and YP models fit a large fraction of the features for which the pH model does not fit. So now we want to start talking about our proposed methods for feature selection and ranking. And the first one is a test for genomic feature effect. And we create a general framework based on the YP model. So ultimately what we're doing is we're testing the null alternative that the parameters equal 0 against the alternative they differ from 0 under the YP model using Kullback-Leibler divergence, so KL divergence. And you can see that general form here. F and F0 are the densities under the alternative and null hypotheses respectively. We're going to use this to develop tests and measures for both feature selection and ranking. So using the density, survival, and hazard functions for the YP model, we're able to come up with the form for IYP, and you can see that form here. Now, on the next slide, I show how this is actually computed. So the estimator of the measure for individual feature J is computed as follows. You can see Zij represents the feature measurement for individual I and feature J. And parameters beta and gamma are estimated after dichotomizing the Jth feature by the median. And we'll talk a little bit about this later, but essentially this I measure can be used for a ranking. There are also 2 special cases. So the benefit of the YP model is that it does have PO and pH as special cases. So if we very simply set gamma equal to 0 in the YP case, we get a form for IPO. And if we set gamma equal to beta in the YP case, we get a form for IPH. So for the PO case, to calculate the measure, we simply replace beta with beta hat, which is estimating using the maximum partial likelihood in the PO model. We can actually also calculate a variance of IPO, and that allows us to create a test statistic. So we get a chi-squared test statistic for this PO measure. Similarly, we can create an IPH and chi-squared test statistic for the pH case. So a little bit more about this I as a ranking measure and test measure. So what I does is it actually quantifies feature effect under the assumption of the pH, PO, or YP models. So I can be calculated for all P measures in a data set and can be used to rank them. But we can also look at the chi-squared test statistics in the pH, PO, and pH cases, and they provide significance tests for each feature. So we can use standard FDR thresholds to select features. Now, the PO-based measures can handle quantitative or dichotomized features, NPH and pH under certain conditions, as well as confounders, where the YP case, IYP, can only handle a single dichotomized feature. Now, the next measure we look at is actually an extension of these I measures, and it's an R-squared measured based on this information divergence. So the first thing we do is we apply a variance stabilizing and normalizing transformation to each feature Z and standardize it. We then define this I tilde as the expectation of I with respect to the marginal distribution of Z, and you can see that form here. And then once that's computed, we can compute an R-squared measure. So R-squared is just 1 minus exponential negative 2 times that I. And this is a quantity for explained randomness. So this R-squared I can be calculated for both the PO and pH cases. We use a Taylor series expansion to do that calculation. We ultimately get the I measures, and you can see their approximations here, and then they get plugged into that general R-squared computation. So we have an R-squared IPO and an R-squared IPH. Our next proposed method is a generalized pseudo R-squared measures, and it's a really unified approach. So we develop an R-squared measure based on the pH, PO, CO, and CH models that can be used to rank features. Each of them is based on the score function, so the derivative of the log partial likelihood for their respective models when beta equals 0. And you can see that general form here. The W is going to be calculated based on the desired model. R is the set of individuals at risk at time TI, and Y bar is the number of subjects at risk at time TI. So basically, we can get an estimate for this U, so this UI hat, using the following form. Delta I is the indicator of failure at time TI, and W hat, which we'll see on the next slide, is the weight that we use to specify each specific model. So if you look at the chart on the next slide, you can see depending on the model of interest, you can use that specific weight. So for the pH model, you would use a weight of 1, for the CH model, a weight of 1 plus log, and then you can see how that gamma 0 and S0 are calculated above. Now, the next step here is we introduce a WI, which is a robust score introduced by Lin and Wei, 1989 paper. You can see the form here. There's more details in the appendix, but essentially the sum of WI is identical to the sum of UI, but the WI are independent. Then you can see we finally get to our generalized pseudo R-squared measure. It has the following form, where K is the number of uncensored failure times. It's a robust score statistic divided by the number of distinct uncensored failure times. It falls between 0 and 1. It does not require model parameter estimates. That's a benefit. It generalizes the measures found in Rome's 2010 and 2011 papers. So R-squared PO and CO are our proposed measures, and R-squared CH and pH are the existing measures from those papers. And one major benefit is its interpretation. So it can be interpreted as the percentage of separability in feature values between those experiencing and not experiencing the event of interest. Oh, one other thing I just wanted to note is there were some small computational corrections for the CO and CH cases, and if you're interested, I can provide more details on that. So the next thing we wanted to look at were the simulations. So we used 2 simulation algorithms to create various survival data sets. We have a scheme 1 and scheme 2. Scheme 1 links survival to the features one at a time. Scheme 2 introduces correlations between features. We simulate 2,000 data sets with 200 subjects and 5,000 mock features for each. And the first 400 features are designed to have an effect on survival. Survival times are generated from the log normal, log logistic, and Weibull models. And we apply all of our proposed methods, including an R-squared LR, which I have not mentioned, which is an R-squared measured based on the log likelihood ratio of the PO model. This is an extension of O'Quigley's work in the 2005 paper. They use the pH model, we use PO, and then all the other proposed methods we've talked about. And then we compare them to the existing methods in Rome paper, and then also a concordance regression method called CONCREG from Dunkler's paper in 2010. We look at average AUC values across the 200 runs, and they are reported on the next 2 slides. So first, we look at scheme 1 and those average AUCs, and we can see that overall across the board, our methods are outperforming existing methods in many cases. Some things to highlight, you can see in yellow that our PO-based measures, our R-squared PO, LR, R-squared IPO, or IPO, are really outperforming the other methods, particularly in the log logistics scenario that you can see highlighted again in yellow. IYP, which I have highlighted in orange in a few situations, is performing better than CONCREG overall. And then particularly in the log normal case and for lower censoring. And then you can also see that our CO and CH R-squared measures perform best in lower censoring and in the log normal case, and they're doing particularly well there compared to the other methods. We see really similar results for scheme 2, which is a more complex simulation scheme, but really similar results. We can see the IYP highlighted in orange is really performing well for lower censoring, particularly in the log normal and log logistic cases. Our IPO and our other PO-based measures are performing well overall. So as a whole, you can see that our methods are performing either similarly or better than the other methods, depending on the situation. The next thing we looked at were some real data examples. So we applied the proposed and existing methods to the ovarian oral data sets 4 and 5, and we ranked the features based on those values. So for this piece, we just looked at the top 500 features selected in each case. And the thing to really note is that you can see if you look at the first Venn diagram, these are all the measures based on PO. So our R-squared IPO, R-squared PO, R-squared LR, and you can see that there's a large overlap between the selected features in that case. Whereas the other methods here, you can see really select fairly independent sets of features. And what we really need to examine is some thresholding criteria for future work. And here you can see the oral data set, a very similar picture of what's going on. Now, another thing we looked at, which I found really interesting, is the number of features selected by chi-squared PO and conc-reg. In most cases, you can see that the chi-squared PO, whether it's quantitative or the dichotomous scenario, selects a larger number of features than the conc-reg from Dunkler's paper. So what this really highlights for us is that the concordance regression as conc-reg is really a tool for feature ranking only, whereas chi-squared PO can be used for feature ranking, but also for selection, based on those p-values. And now I'm just going to conclude. So ultimately what we've done is we used genomic data to demonstrate some of the potential challenges, such as high dimensionality, censoring, and the presence of NPH. We then proposed 2 frameworks for feature selection to address NPH. We looked at IYP, which is a simple function of the estimates of the model parameters based on KL divergence, as special cases based on the PO and pH models. We looked at the R-squared measure based on the I measures. They're derived by IPO and IPH. They're simple functions of the estimates of the model parameters. Then we have the pseudo R-squared measures using the pH, PO, CO, and CH models. They're derived from the partial likelihood for their respective models. They require no parameter estimation, and they measure the percentage of separability in genomic features between the event and non-event groups. So it has a nice interpretation. We also had our R-squared LR measure, which was derived from the law likelihood ratio from the PO model. And overall, we showed that our proposed methods outperformed existing methods in simulated scenarios. Our work is currently published in bioinformatics, and you can see the citation here. There's a list of references, and I want to thank you all so much for your time. And I have some further details in the appendix if anyone is interested. Thank you so much, and I look forward to questions.